In 1977, two spacecraft left Earth carrying a message in a bottle. They were expected to last only a few years. Yet, 47 years later, Voyager 1 and Voyager 2 are still speaking from more than 23 billion kilometers away. What they discovered shattered every prediction. The edge of our solar system is not cold, quiet, or round, but a turbulent battlefield of invisible forces. What happens at the very edge of home? And why did two tiny machines change everything we thought we knew? If this sparks your curiosity, consider subscribing to explore further. Space, as we've been told since childhood, is cold. Absolute zero, the void where heat goes to die. And for most of the universe, that's true. Atoms drift apart, starlight fades, and everything cools towards silence. But at the boundary of our solar system, where the Voyager probes crossed into interstellar space, they found something no one predicted: a wall of plasma burning at 250,000 degrees Celsius. Not cold, not silent, a furnace invisible and roaring, marking the place where our sun's influence ends and the galaxy begins. This wasn't supposed to happen. The models, the equations, the decades of planning, none of it prepared scientists for this. And when Voyager 1 sent back the numbers in 2004, crossing what's called the Termination Shock at 94 times the distance from Earth to the Sun, the data seemed wrong. Too hot, too violent. But Voyager 2 confirmed it 3 years later, piercing the same boundary at 84 times that distance, a billion kilometers closer, revealing that this wall isn't even symmetrical. It bends, it warps, and it burns. To understand why, you need to picture the solar wind not as a metaphor but as a physical thing. The sun doesn't just shine light, it bleeds. Every second, it hurls 1 trillion kilograms of plasma into space. Protons, electrons, stripped atoms, moving at 1.6 million kilometers per hour. That's fast enough to circle Earth 7 times in a single second. And this wind doesn't stop. It doesn't pause. It rushes outward in all directions, filling the solar system like an ocean current made of fire. For billions of kilometers, that wind expands freely, cooling, as it spreads, thinning as it races away from the Sunday. The planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, all of them sit inside this river of particles. We're bathed in it, protected by it. And we never feel it, because Earth's magnetic field deflects most of it away, channeling the charged particles toward the poles where they ignite as auroras, green curtains of light dancing over Arctic skies. But out past Neptune, past Pluto, past the frozen rocks of the Kuiper Belt, the solar wind keeps moving. And eventually, it hits resistance. Not a wall made of stone or metal, but something just as real: the interstellar medium. The space between stars isn't empty. It's filled with gas, mostly hydrogen, ancient and thin, drifting through the galaxy at roughly 0.1 atoms per cubic centimeter. Compare that to the solar wind, which at the same distance carries about 10 particles per cubic centimeter. The solar wind is 100 times denser, 100 times faster, and when these two forces meet, they collide. That collision is the termination shock. The physics here is straightforward, even if the result is shocking. When the solar wind slams into the interstellar medium, it's moving faster than the speed of sound, supersonic in cosmic terms. And just like a jet breaking the sound barrier creates a shockwave that rattles windows and shakes the ground, the solar wind creates a shockwave in space. Except instead of sound, it's plasma. And instead of air, it's the fabric of the heliosphere, the bubble of influence our sun carves out in the galaxy. At the shockwave, the solar wind doesn't just stop. It compresses. All that kinetic energy, the energy of motion of particles racing at hypersonic speeds, converts into heat. Instantly, violently, the temperature spikes to 250,000 degrees Celsius, 50 times hotter than the surface of the sun itself. And this isn't a brief flash. It's a permanent feature, a glowing boundary surrounding the entire solar system, held in place by the constant pressure of the solar wind pushing out and the interstellar medium pushing back. Voyager 1 crossed this threshold on December 16, 2004. It had been traveling for 27 years, covering 14 billion kilometers, and suddenly its instruments registered a surge. The density of particles around it doubled. The temperature spiked. The magnetic field twisted, and the speed of the solar wind, which had been roaring past at supersonic velocity, dropped to subsonic. The wind, for the first time since leaving the sun, slowed down, not because it wanted to, because it had to. It hit a wall it couldn't break through. Voyager 2 followed in 2007, crossing at a different latitude, closer to the solar equator, and found the same phenomenon. But the boundary was 10 billion kilometers nearer to the Sunday. This confirmed what scientists suspected, but hadn't proven the heliosphere isn't a perfect sphere. It's asymmetric, squeezed and stretched by forces outside our control. The northern hemisphere bulges outward, the southern hemisphere pulls inward, and the reason has everything to do with what lies beyond. The interstellar medium isn't uniform. The galaxy is filled with clouds, vast regions of gas and dust, some dense, some sparse, all drifting through space at different speeds. Our solar system is currently moving through one of these clouds called the local interstellar cloud at 83,000 kilometers per hour. That motion creates pressure like a car pushing through water, and that pressure shapes the heliosphere. Where the cloud is denser, the heliosphere compresses. Where it's thinner, the heliosphere expands. The result is a boundary that shifts, breathes, and bends depending on where you cross it. But the heat that's the revelation. Before Voyager, scientists assumed the edge of the solar system would be cold, a gradual cooling as the sun's warmth faded into the void. Instead, they found a furnace, and the reason is energy conversion. Every particle of the solar wind carries momentum. When it hits the interstellar medium and stops, that momentum doesn't disappear. It transforms. Motion becomes heat. Speed becomes temperature. And the result is a glowing wall of plasma, invisible to the naked eye, but blazing in the data Voyager sends back. If you could somehow stand at the termination shock, protected impossibly from the vacuum and radiation, you wouldn't feel cold. You'd vaporize. The plasma around you would be hotter than the surface of any star you can see in the night sky. And yet this heat doesn't radiate inward. It doesn't warm the planets. It stays locked at the boundary, a consequence of physics, a byproduct of collision. The solar system remains cold. The heliosphere remains dark. But at the edge, where our sun's breath meets the galaxy's indifference, there's fire. Voyager's discovery didn't just rewrite textbooks. It revealed something unsettling. We don't know our own neighborhood as well as we thought. The models were wrong. The predictions missed the mark. And the universe once again proved stranger than the equations suggested. The termination shock isn't a gentle transition. It's a battleground, a place where two cosmic forces grind against each other, and the friction creates heat we never anticipated. But the shock isn't the end of the story. It's just the first layer. Beyond it lies another region, another mystery, a place Voyager would spend years crossing, a place where the rules change again, where particles from the sun and particles from the galaxy flow side by side, neither winning, neither losing, locked in a strange and temporary truce. And what Voyager heard there in the darkness beyond the shock was even stranger, a sound, a hum, the voice of interstellar space itself. Silence is supposed to be the default state of space. No air means no sound waves, no vibrations traveling ear to ear. The vacuum swallows everything. And yet, when Voyager 1 crossed into interstellar space in August 2012, it began recording something that, when converted into audio frequencies, humans can hear. Sounds like this, a low, persistent hum, not loud, not dramatic, just there, constant, unbroken, the background noise of the galaxy. Scientists call them plasma waves, oscillations in the charged particles that fill the space between stars. But when NASA's engineers translated the data into sound, what emerged was unsettling. A tone so steady, so relentless, it felt less like a natural phenomenon and more like a signal, a heartbeat. The galaxy breathing. Plasma in this context isn't fire. It's the fourth state of matter beyond solid, liquid, and gas, where electrons have been stripped away from atoms, leaving behind a soup of charged particles that respond to magnetic and electric fields. And in space, plasma doesn't just float, it vibrates. When disturbances pass through it, shockwaves from the sun gusts of interstellar wind collisions between magnetic field lines, the plasma ripples, creating waves that propagate outward, like sound through water. Voyager's instruments can detect these waves because they generate tiny fluctuations in the electric field around the spacecraft. The antenna picks up the oscillations, measures their frequency, and transmits the data back to Earth. And what the data revealed once Voyager crossed the heliopause, the true boundary of the heliosphere beyond the termination shock, was a constant hum at a frequency around 300 Hz. Low, steady, uninterrupted. But here's what makes it strange: the hum isn't random. It has structure. Inside the heliosphere, before Voyager crossed over, the plasma waves were chaotic bursts of activity. Whenever the sun belched out, a coronal mass ejection followed by silence, then more bursts. The pattern was irregular, tied to the sun's 11-year cycle of magnetic flips and solar storms. But outside, in interstellar space, the hum is constant. No bursts, no silence, just a low droning oscillation that suggests the interstellar medium itself is vibrating all the time everywhere. The frequency tells us about density. Plasma waves oscillate faster when there are more particles packed into a given volume. At 300 Hz, Voyager's measurements correspond to a plasma density of roughly 0.1 electrons per cubic centimeter. Exactly what scientists predicted for the local interstellar cloud. The patch of gas the solar system is currently drifting through. But the remarkable thing isn't just that the density matches the predictions. It's that this density is so uniform. Across millions of kilometers, across years of measurements, the hum barely changes. The interstellar medium, at least in this region, is extraordinarily smooth. In 2013, a year after Voyager 1 crossed the heliopause, NASA released audio files of these plasma waves converted into frequencies the human ear can process. The sound is unsettling. It's not musical. It's not melodic. It's mechanical. A deep, resonant drone that feels ancient, indifferent, like the hum of an engine running in the basement of the universe. And once you hear it, it's hard to shake the feeling that space isn't empty. It's full of energy, full of motion, full of something we've only just begun to understand. The interstellar medium, it turns out, isn't quiet. It's alive with activity, magnetic fields, twisting particles colliding, shockwaves from distant supernovae rippling outward across light years. And Voyager, with its tiny instruments and decades-old technology, is the only human-made object that's ever been there to listen. The hum also reveals something about temperature. In plasma physics, temperature isn't just about how hot something feels, it's about how fast particles are moving. The faster they move, the higher the temperature. And the plasma waves Voyager detects carry information about this motion. Analysis of the wave frequencies shows that the electron temperature in the interstellar medium is roughly 5,000 to 10,000 degrees Celsius. Not the 250,000 degrees of the termination shock, but still far hotter than anything we'd call cold. This temperature represents the kinetic energy of electrons jittering around, bouncing off each other, maintaining the constant vibration that produces the hum. But the hum isn't just constant, it changes. In 2017, 5 years after entering interstellar space, Voyager 1 detected a sudden spike in the frequency of the plasma waves. The hum, which had been steady at 300 Hz, jumped to 340 Hz, a jump of about 13%. The cause? A coronal mass ejection from the sun, a massive burst of charged particles that had been expelled years earlier, had finally reached the heliopause and pushed outward into interstellar space, compressing the plasma and causing it to vibrate faster. The event lasted weeks. Then slowly, the frequency dropped back down, but not all the way. The hum settled at a slightly higher pitch than before, as if the interstellar medium had been permanently jostled by the intrusion. And this pattern repeated in 2020, and again in 2023 each time the sun sent out a major eruption. Months or years later, Voyager would detect a corresponding increase in the plasma oscillations beyond the heliopause. What this means is that the boundary isn't sealed. The heliosphere and the interstellar medium are in constant contact, exchanging energy, influencing each other. The sun's outbursts don't stop at the heliopause, they leak through, disturbing the galaxy's background hum like a stone thrown into a still pond. And Voyager, sitting in the ripples, measures the result. These pulses also travel. When the Sun ejects a coronal mass ejection, the burst of plasma expands outward at speeds of several hundred kilometers per second. It takes roughly 2 to 3 years for that disturbance to reach the heliopause from the Sun, a distance of about 120 astronomical units. And once it crosses the heliopause, it continues propagating into interstellar space, creating a bubble of compressed plasma that pushes outward, raising the local density and frequency of plasma waves as it goes. Voyager detects these bubbles as they pass, each one a ghostly echo of solar activity from years before. Voyager 2, which crossed into interstellar space in November 2018. 6 years after Voyager 1 confirmed the same phenomenon. The hum is universal. It's not unique to the patch of space Voyager 1 entered. It's a feature of the interstellar medium itself, at least in this region of the galaxy. And the frequency is consistent 300 to 350 Hz, depending on recent solar activity corresponding to plasma densities of about 0.1 particles per cubic centimeter. But there's another layer to this. Between the bursts, the sudden spikes caused by solar eruptions, Voyager occasionally detects something else, short, sharp oscillations at much higher frequencies, lasting only seconds or minutes. These aren't caused by the Sunday. They're local disturbances, possibly from magnetic reconnection events, moments when magnetic field lines in the interstellar medium snap and reconnect, releasing bursts of energy like miniature lightning strikes in space. No one predicted this. The models assumed interstellar space would be smooth, homogeneous, a vast ocean of dilute hydrogen with little variation. But what Voyager is revealing is texture, structure, turbulence. The interstellar medium isn't a calm sea. It's choppy, filled with eddies and currents and sudden bursts of activity that we're only beginning to map. And the sound, the hum, is the closest thing we have to hearing the galaxy's voice. Not the stars themselves, which are too far apart to communicate, but the medium between them, the fabric of space, made audible. NASA's Jet Propulsion Laboratory in Pasadena receives Voyager's data once every few weeks, downloaded during scheduled communication windows that last a few hours. The spacecraft transmits at 23 watts, less power than a refrigerator light bulb, and the signal, after traveling 23 billion kilometers, arrives at Earth's antennas, so faint it's measured in femtowatts, 1/4,000,000th of a watt. And yet the data is clean, readable, enough to reconstruct the hum second by second, year by year. The engineers who built Voyager never imagined it would last this long. The plasma wave instrument was designed for a 5-year mission, maybe 10 if they were lucky. It's been running for 47 years. The circuits are degrading. The power supply is fading. But the instrument still works, still listens, still sends back the hum of interstellar space. In 2024, a new analysis of Voyager's plasma wave data revealed something unexpected, a rhythmic pattern in the hum, repeating every 26 days. The frequency doesn't change, but the amplitude, the intensity of the oscillations pulses in a cycle that matches the rotation period of the Sunday, even 20 billion kilometers away beyond the heliopause, in a realm the Sun's magnetic field no longer controls. Voyager is still hearing echoes of home. The Sun's rotation stirs the heliosphere, and those ripples propagate outward, reaching the interstellar medium and modulating its hum. The galaxy, it seems, remembers, and Voyager is there to document it alone in the dark, recording the sound of a place no human will visit for centuries, if ever. But the hum raises a question: if the interstellar medium is this active, this textured, this full of energy, what does it do to the heliosphere itself? How does the galaxy shape the bubble we live in? And if the hum can change based on what the Sun does, what happens when the Sun moves through different regions of the galaxy? Denser clouds, stronger magnetic fields, hotter or colder environments. The heliosphere, the bubble of space, dominated by the Sun's magnetic field and solar wind, should be round. A sphere. That's what the name implies. That's what every diagram in every textbook shows: a neat, symmetrical bubble surrounding the solar system, protecting it from the interstellar medium. And for decades, that's what scientists believed. Then Voyager 1 and Voyager 2 crossed the heliopause at different distances. 94 astronomical units for Voyager 1, 84 astronomical units for Voyager 2, and the symmetry shattered. The heliosphere isn't round. It's warped, stretched, compressed into a shape that looks less like a sphere and more like a croissant, or a bullet, or a comet with a long tail streaming behind. The discovery came slowly. Voyager 1 crossed the heliopause on August 25, 2012. Scientists knew it had crossed because three things changed simultaneously. The density of galactic cosmic rays, high-energy particles from outside the solar system spiked by 30%. The intensity of solar particles dropped to near zero, and the direction of the magnetic field shifted, aligning with the interstellar field rather than the Sun's. Voyager 1 was officially in interstellar space. But where exactly was the heliopause? The spacecraft's instruments couldn't measure distance directly. They could only detect changes in the environment. So scientists used the data to estimate roughly 122 astronomical units from the Sun in the direction Voyager 1 was traveling, which corresponded to about 18 billion kilometers. Then 6 years later, Voyager 2 crossed, November 5, 2018. Same three signatures: cosmic rays up, solar particles down, magnetic field flip. But Voyager 2 was only 119 astronomical units from the Sun, 3 astronomical units closer, about 450 million kilometers nearer than Voyager 1's crossing point. At first, this seemed like a measurement error, but the data was consistent. Both spacecraft had crossed the same boundary, the heliopause, but at different distances, which meant the boundary itself wasn't uniform. The heliosphere wasn't a perfect sphere. It was asymmetric, bulging in some directions and compressed in others. To understand why, you have to zoom out. The Sun isn't stationary. It's moving through the galaxy at 83,000 kilometers per hour, heading toward a point in the constellation Hercules. And as it moves, it's plowing through the interstellar medium, the thin soup of hydrogen, helium, and trace elements that fills the space between stars. That motion creates pressure. The interstellar medium pushes back against the heliosphere, compressing it on the side, facing the Sun's direction of travel, and stretching it out behind like a comet's tail. This phenomenon is called ram pressure, and it's the same reason comets have tails as they approach the Sun. The solar wind pushes against the gas and dust surrounding the comet's nucleus, creating a long, glowing tail that always points away from the Sunday. The heliosphere works the same way, except instead of solar wind creating the tail, it's the Sun's motion through the interstellar medium. The nose of the heliosphere, the part facing the direction of motion, experiences the highest pressure. The interstellar medium piles up there, compressing the heliopause inward. Behind the Sun, in the opposite direction, the pressure is lower. The solar wind can expand farther before it encounters resistance. The result is a teardrop shape, blunt at the front, elongated at the back. But there's another force at play: the interstellar magnetic field. The galaxy has its own magnetic field, weak only a few microgauss in strength, but vast, stretching across thousands of light years. And this field isn't aligned with the Sun's motion. It's oriented at an angle roughly perpendicular to the Sun's trajectory. As the heliosphere moves through this field, the magnetic pressure squeezes it from the sides, compressing it along certain axes and allowing it to expand along others. The result is a shape that's neither round nor symmetrical. Computer models refined with data from Voyager and from NASA's Interstellar Boundary Explorer IBEX, a satellite that maps the heliosphere from Earth orbit by detecting neutral atoms that originate at the boundary, suggest the heliosphere looks something like a croissant. The nose of the heliosphere, facing the direction of the Sun's motion, is blunt and compressed. The sides are pinched inward by the interstellar magnetic field, and the tail streaming behind is long and twisted, possibly extending hundreds of astronomical units so far that no spacecraft has ever measured it directly. Data from IBEX collected over more than a decade revealed another surprising feature: a ribbon of enhanced emission stretching across the sky, marking a region where neutral atoms are being created at a higher rate than elsewhere. This ribbon traces the boundary where the Sun's magnetic field and the interstellar magnetic field are nearly perpendicular to each other. The ribbon's shape and position confirm that the interstellar magnetic field is pressing against the heliosphere asymmetrically, creating localized regions of higher pressure and density. Voyager 1 crossed near the nose, where the heliosphere is widest. Voyager 2 crossed farther south, where the heliosphere is narrower, compressed by the interstellar field. That's why the distances were different. The boundary itself is at different distances depending on where you measure it. This asymmetry has consequences. The heliosphere isn't just a static bubble, it's a dynamic structure that changes shape over time. Every 11 years, the sun's magnetic field flips, north becomes south, south becomes north. And every time the field flips, the heliosphere responds. The solar wind strengthens or weakens, depending on the phase of the solar cycle, and the heliopause moves inward or outward accordingly. During solar maximum, when the sun is most active, covered in sunspots ejecting frequent coronal mass ejections, the solar wind is strong and turbulent. The heliosphere expands, pushing the heliopause outward by several astronomical units. During solar minimum, when the sun is quiet with few sunspots and calm magnetic activity, the solar wind weakens. The heliosphere contracts, pulling the heliopause inward. Voyager 1 crossed the heliopause during the declining phase of solar cycle 24, as the sun transitioned from maximum to minimum. Voyager 2 crossed during solar minimum itself. This timing difference may partly explain why Voyager 2's crossing point was closer to the sun. The heliosphere had contracted by the time Voyager 2 arrived at the boundary. In 2024 data from NASA's Solar Orbiter mission, a spacecraft studying the sun's polar regions revealed that the solar wind has weakened by about 30% compared to the 1970s when Voyager was launched. This means the heliosphere is shrinking. The heliopause is creeping inward, closer to the sun as the pressure from the interstellar medium gains the upper hand. If this trend continues, the heliopause could move inward by 10 to 15 astronomical units over the next few decades, closer to the orbit of Pluto, which ranges from 30 to 50 astronomical units from the Sunday. This wouldn't threaten Earth directly. We're still 93 astronomical units inside the boundary at our position, but it would increase the flux of galactic cosmic rays entering the solar system, raising radiation levels for spacecraft and astronauts traveling beyond Earth's magnetic field. Climate models suggest that increased cosmic ray flux could potentially affect Earth's atmosphere as well, though the effects would be subtle. Cosmic rays, when they enter the atmosphere, ionize molecules and may contribute to cloud formation. A significant increase in cosmic ray intensity, say a doubling over several centuries, could alter cloud cover patterns and influence global temperatures by a fraction of a degree. It's a small effect easily overwhelmed by other climate drivers, but it demonstrates that the heliosphere's shape and strength have real consequences for our planet. But the heliosphere's shape isn't the only surprise. The boundary itself isn't sharp. Voyager didn't cross a clean line and suddenly find itself in interstellar space. Instead, it passed through a transition region, a zone where the properties of the heliosphere and the interstellar medium blended together, overlapping in ways that defied the models. This transition region, which scientists now call the heliosheath, is where the solar wind slows down but doesn't stop entirely. It's where particles from the sun and particles from the galaxy mix, flowing in different directions, sometimes moving parallel to the boundary instead of perpendicular to it. And it's where Voyager spent years drifting through a cosmic no man's land, trying to figure out which side it was on. The heliosheath turned out to be much thicker than expected. Voyager 1 spent nearly 9 years crossing it, from 2004, when it entered the Termination Shock, to 2012, when it finally exited the heliopause. That's roughly 30 astronomical units of transition zone, a region where the rules are unclear, where particles obey neither the sun's commands nor the galaxy's, where everything is in flux. Computer simulations run in 2023, incorporating all of Voyager's measurements plus IBEX data, suggest the heliosheath is not just thick but layered. There are sub-regions within it, where the plasma density varies, where magnetic field lines twist into complex geometries, where shockwaves from old coronal mass ejections still linger, trapped between the termination shock and the heliopause. It's not a simple gradient from solar to interstellar, it's a turbulent mixing zone, a battlefield where two cosmic domains collide and neither fully dominates. And within that zone, Voyager discovered something even stranger: a magnetic highway, a structure no one had predicted. a place where the boundary between the heliosphere and interstellar space became porous, allowing particles to flow through in organized streams, channeled by magnetic field lines that connected the two domains like a bridge between worlds. But understanding that highway and what it means for the boundary itself requires looking closer at how magnetic fields work in space and why they matter so much at the edge of the solar system. In the final months before Voyager 1 crossed the heliopause, something strange started happening. The spacecraft's instruments detected a sudden increase in the number of galactic cosmic rays particles from outside the solar system while simultaneously recording a drop in solar particles. But the magnetic field, the key indicator that should have flipped when Voyager crossed the boundary, didn't change. It stayed aligned with the sun's field stubbornly pointing in the wrong direction. For 18 months, from January 2012 to August 2012, Voyager drifted through this paradox. Cosmic rays poured in from the galaxy, solar particles leaked out into interstellar space, and the magnetic field refused to cooperate. The spacecraft was in two places at once: inside the heliosphere, according to the magnetic field, outside the heliosphere, according to the particles. Scientists at NASA had no explanation. The models didn't account for this. The boundary was supposed to be clear inside or outside, not both. But Voyager was measuring both. And it wasn't until August 2012, when the magnetic field finally flipped and aligned with the interstellar field, that Voyager officially crossed over. Only then did NASA announce Voyager 1 has left the solar system. But what was that 18-month transition? What was Voyager measuring? The answer came from a closer analysis of the data, combined with theoretical models of magnetic reconnection. A process where magnetic field lines from two different regions break, reconnect, and reconfigure, allowing particles to flow along new paths. And what emerged was a picture of a structure scientists eventually named the magnetic highway. A layer at the edge of the heliosphere where the sun's magnetic field and the galaxy's magnetic field ran parallel to each other, creating channels through which particles could travel freely without crossing the main boundary. Think of it like this: the heliopause is supposed to be a wall. On one side, the sun's domain, on the other, the galaxy's domain. But instead of a solid wall, what Voyager found was a fence with gaps, magnetic field lines that connected both sides, allowing particles to flow through in specific directions, while still maintaining some separation between the two regions. Galactic cosmic rays traveling along these field lines could enter the heliosphere without fully crossing the heliopause. Solar particles following the same lines could escape into interstellar space without technically leaving. The two populations coexisted, flowing in parallel like two streams of traffic on a highway, moving in opposite directions but sharing the same road. This structure, the magnetic highway, is roughly half an astronomical unit thick, which translates to about 75 million kilometers. For Voyager 1, traveling at roughly 60,000 kilometers per hour relative to the Sun, crossing this zone took 18 months. For Voyager 2, which crossed the heliopause 6 years later, the magnetic highway was narrower, only a few months of travel time, but it was still there, still measurable, still channeling particles between the heliosphere and the interstellar medium. The existence of the magnetic highway reveals something fundamental about magnetic fields in space. They don't respect boundaries the way matter does. A particle can only be in one place at a time, but a magnetic field line can stretch across regions, connecting distant locations, creating pathways for particles to follow. And when two magnetic fields meet, like the sun's field and the galaxy's field, they don't just push against each other. They interact, they twist, they reconnect. And in the process, they create structures like the magnetic highway places, where the distinction between inside and outside blurs. Magnetic reconnection itself is a violent process. When field lines break and reconnect, they release energy, sometimes enormous amounts of it. On the Sun, magnetic reconnection drives solar flares and coronal mass ejections, events that can release as much energy as billions of nuclear bombs in a matter of minutes. In Earth's magnetosphere, reconnection triggers auroras, as particles accelerated by the reconnection process slam into the upper atmosphere and light up the sky. At the heliopause, reconnection happens more slowly, more gently, but it's happening constantly. The Sun's magnetic field and the galaxy's magnetic field are always in contact, always interacting, always exchanging energy and particles through reconnection events that occur along the boundary. And the magnetic highway is the result, a semi-permanent structure created by the cumulative effect of countless reconnection events, each one slightly altering the configuration of field lines, each one opening new channels for particles to flow through. Voyager 2's crossing provided crucial confirmation. When it entered the magnetic highway in October 2018, it detected the same pattern, cosmic rays increasing, solar particles decreasing, but the magnetic field still aligned with the Sunday. And just like Voyager 1, Voyager 2 spent months in this transition zone before the field finally flipped in November 2018, marking the official crossing into interstellar space. But Voyager 2 also detected something Voyager 1 didn't. A series of short, intense bursts of magnetic activity, sharp spikes in the magnetic field strength, lasting only minutes or hours, interspersed throughout the magnetic highway. These bursts are likely the signature of active reconnection events, moments when the field lines are actively breaking and reconfiguring, releasing pulses of energy that ripple outward through the surrounding plasma. The discovery of these bursts suggests the magnetic highway isn't static. It's dynamic, constantly evolving as the sun's magnetic field and the galaxy's magnetic field push against each other, reconnect and push again. The structure is maintained by a balance of forces: the outward pressure of the solar wind, the inward pressure of the interstellar medium, and the tension in the magnetic field lines that connect them. And that balance shifts over time, responding to changes in the solar wind, changes in the sun's magnetic field, and changes in the interstellar environment. In 2023, new data from Voyager 1 revealed another layer to this story. 10 years after crossing the heliopause, Voyager detected a sudden sharp increase in the magnetic field strength. A jump of about 10% that lasted several weeks before returning to normal. The cause wasn't immediately clear, but one possibility is that Voyager had crossed a magnetic filament in the interstellar medium. A narrow, dense strand of magnetic field, possibly created by a distant supernova shockwave that had drifted through the region. If that's the case, it means the interstellar medium isn't just filled with gas and dust. It's threaded with magnetic structures left over from ancient stellar explosions that persist for millions of years, slowly drifting through the galaxy, shaping the environment through which the sun and its heliosphere move. The magnetic highway, then, isn't just a feature of the heliopause. It's a window into the larger magnetic architecture of the galaxy, a place where the local field of the sun intersects with the global field of the Milky Way, and where particles from both domains flow together briefly before separating again. But the magnetic highway also raises a deeper question. If particles can flow through the boundary so easily channeled by magnetic field lines, then how effective is the heliosphere as a shield? How much does it actually protect us from the galaxy's radiation? And what happens when the shield weakens, or when the sun's activity changes? Before Voyager launched, scientists expected to find not one boundary at the edge of the solar system, but two. The first would be the heliopause, the place where the solar wind stops and the interstellar medium begins. And the second, farther out, would be the bow shock, a shockwave in the interstellar medium created by the sun's motion through the galaxy, similar to the shockwave a boat creates as it moves through water. Every object moving through a fluid faster than the speed of sound in that fluid creates a bow shock. Supersonic jets create them. Spacecraft re-entering Earth's atmosphere create them. And the sun, moving through the interstellar medium at 83,000 kilometers per hour, faster than the speed of sound in the interstellar plasma, should create one too. The models predicted it would form about 200 to 300 astronomical units ahead of the sun in the direction of the sun's motion. It would be a region of compressed, heated plasma where the interstellar medium piles up as the heliosphere pushes through it, creating a standing wave that propagates ahead of the sun's motion like the bow wave of a ship. But Voyager never found it. Voyager 1, now more than 160 astronomical units from the sun, has detected no sign of a bow shock. Voyager 2, at 135 astronomical units, hasn't found it either. And data from IBEX, which maps the structure of the heliosphere from Earth orbit by detecting neutral atoms that originate at the boundary, shows no evidence of a bow shock anywhere in the expected region. The bow shock, it seems, doesn't exist, at least not here. not now. And the reason has to do with the density of the interstellar medium and the fact that the Sun is currently moving through an unusually empty region of the galaxy. The local interstellar cloud, the patch of space the solar system is currently traversing, is part of a larger structure called the local bubble. A cavity in the interstellar medium, roughly 1,000 light-years across, that was carved out by a series of supernova explosions 10 to 20 million years ago. These explosions, stars much more massive than the Sun, reaching the end of their lives and detonating, blew away most of the gas and dust in the region, creating a bubble of hot, rarefied plasma with a density of only about 0.1 atoms per cubic centimeter. For comparison, the typical density of the interstellar medium in the galactic disk is about 1 atom per cubic centimeter, 10 times denser. And in molecular clouds, where new stars are forming, the density can reach hundreds or thousands of atoms per cubic centimeter. But here in the local bubble, the density is so low that the Sun's motion doesn't create a bow shock. The interstellar medium is too thin, too diffuse. The Sun plows through it like a car driving through fog. There's resistance, but not enough to create a shockwave. This is lucky for us. If the Sun were moving through a denser region of the galaxy, the bow shock would compress the interstellar medium, funneling more galactic cosmic rays toward the heliosphere and potentially increasing the radiation flux inside the solar system. The heliosphere would also be smaller, more compressed, with the heliopause closer to the sunday. And that would mean less shielding from cosmic rays, higher radiation levels for the planets, and a harsher environment for life. But because we're in the local bubble, the heliosphere is larger, more extended, and the absence of a bow shock means the transition from the heliosphere to the interstellar medium is relatively smooth. There's no additional compression, no additional heating, no additional obstacle for Voyager to cross. Still, the absence of the bow shock surprised scientists. The models had predicted it with such confidence that its non-existence required a rethinking of how the Sun interacts with its environment. And it raised a new question: if there's no bow shock now, will there be one in the future? The answer is yes, probably. The Sun isn't stationary within the local bubble. It's drifting toward the edge, moving at 26 kilometers per second relative to the surrounding medium. In about 20,000 to 30,000 years, the solar system will exit the local bubble and enter a denser region of the interstellar medium, possibly the edge of the local interstellar cloud, or the boundary of the loop-eye bubble, another cavity created by more recent supernovae. When that happens, the density will increase. The interstellar medium will push back harder against the heliosphere, and the Sun's motion will finally be fast enough relative to the density to create a bow shock. The heliosphere will compress possibly by as much as 20%. The heliopause will move inward closer to the orbits of the outer planets, and the flux of galactic cosmic rays entering the solar system will increase, raising radiation levels throughout the heliosphere. For Earth, the effects will be subtle. Our magnetic field will still protect us from most of the radiation, but for spacecraft traveling beyond Earth's orbit, and for any future missions to the outer solar system, the environment will be noticeably more hostile. Data from the European Space Agency's Gaia mission, which has mapped the positions and motions of over 1 billion stars in the Milky Way, confirms this picture. Gaia's data shows that the Sun is currently near the center of the local bubble in one of the least dense regions of the galaxy, within hundreds of light-years. We're in a calm spot, a pocket of relative emptiness, and we've been here for about 5 million years, long enough for the heliosphere to have expanded to its current size. But the local bubble isn't permanent. It's expanding, cooling, and eventually it will dissipate as the hot gas inside it cools and mixes with the surrounding interstellar medium. When that happens, tens of millions of years from now, the density around the Sun will increase again and the heliosphere will shrink accordingly. In the meantime, the absence of the bow shock tells us something important. The Sun's environment is unusually benign. We're protected not just by the heliosphere, but by our location in the galaxy. We're in a safe zone, a bubble within a bubble, shielded from the worst of the galaxy's radiation by both the Sun's magnetic field and the emptiness left behind by ancient supernovae. But that shielding isn't absolute. Even without a bow shock, galactic cosmic rays still reach the heliosphere. They still penetrate the heliopause, And Voyager's measurements show just how much radiation is out there waiting on the other side of the boundary. When Voyager 1 crossed the heliopause in August 2012, the instruments detected an immediate change. The intensity of galactic cosmic rays increased by 30% within a week. By the time Voyager had been in interstellar space for a month, the increase had reached 50%. And within a year, cosmic ray levels were 3 times higher than they had been inside the heliosphere. This wasn't a surprise. Scientists expected cosmic ray levels to rise once Voyager left the Sun's protective bubble, but the speed and magnitude of the increase was startling. It confirmed what the models had predicted, but hadn't fully quantified. The heliosphere is a shield, a critical life-sustaining barrier that blocks 70 to 90% of the galaxy's most dangerous radiation. Galactic cosmic rays are high-energy particles, mostly protons, but also heavier atomic nuclei like helium, carbon, and iron that originate outside the solar system. Some come from supernova remnants, the expanding shockwaves of exploded stars that accelerate particles to nearly the speed of light. Others come from more exotic sources, pulsars, black holes, active galactic nuclei. And a few, the most energetic ones, may come from beyond our galaxy, from collisions between galaxies or from jets ejected by supermassive black holes. These particles travel through the galaxy at relativistic speeds, meaning they're moving fast enough that Einstein's theory of relativity starts to matter. At these speeds, time slows down for the particle distances contract, and the energy carried by the particle becomes enormous enough to shatter atomic nuclei, break chemical bonds, and damage DNA. For life on Earth, this radiation would be lethal if it reached the surface in full strength, but it doesn't. The heliosphere blocks most of it. The solar wind flowing outward from the Sun creates a current of charged particles that deflects incoming cosmic rays, bending their trajectories and scattering them away from the inner solar system. The Sun's magnetic field embedded in the solar wind acts like a maze. Cosmic rays that try to penetrate the heliosphere have to navigate a tangled web of field lines, and most of them get turned around before they reach the planets. The result is that Earth receives only about 10 to 30% of the cosmic ray flux that exists in interstellar space. And of that reduced amount, most is blocked by Earth's own magnetic field and atmosphere. By the time cosmic rays reach the surface, their intensity has been reduced by a factor of 1,000 or more. But without the heliosphere, Earth would be exposed. The cosmic ray flux would increase by a factor of 3 to 10. The atmosphere would absorb some of it, but not all. Surface radiation levels would rise. The rate of DNA damage in living organisms would increase. Cancer rates would climb. Mutation rates would accelerate. And over long timescales, millions of years, the increased radiation might make complex life harder to sustain. This isn't speculation. We know this happens because we can see it elsewhere. Mars, for example, lost its global magnetic field about 4 billion years ago. Without a magnetic field to deflect the solar wind, Mars's atmosphere was gradually stripped away by solar and cosmic radiation, leaving the planet cold, dry, and barren. The surface of Mars today is bathed in cosmic rays. Radiation levels there are roughly 50 times higher than on Earth, high enough to pose a serious risk to human explorers. The Moon, which has no magnetic field and no atmosphere, is even worse. Cosmic ray exposure on the lunar surface is more than 100 times higher than on Earth. Astronauts on the Moon during the Apollo missions were exposed to significant radiation doses, manageable for short stays, but potentially dangerous for extended missions. Voyager's measurements confirm that interstellar space is far more hostile than the solar system's interior. The cosmic ray flux Voyager detects is roughly equivalent to what an astronaut would experience on the surface of Mars, except without any atmosphere to provide even partial shielding. For future missions beyond the heliosphere, if humanity ever builds spacecraft capable of interstellar travel, radiation shielding will be one of the biggest challenges. The longer the mission, the more radiation exposure, and the higher the risk of cancer, cataracts, and other radiation-induced illnesses. But the cosmic rays Voyager measures aren't constant. They vary with the solar cycle. Every 11 years, the Sun's magnetic field flips north, becomes south, south becomes north, and the structure of the heliosphere changes. During solar maximum, when the Sun is most active, the solar wind is stronger, the magnetic field is more tangled, and cosmic ray penetration into the heliosphere is reduced. During solar minimum, when the Sun is quieter, The solar wind weakens, the magnetic field becomes more ordered, and cosmic rays penetrate more easily. Voyager 1 crossed the heliopause during the declining phase of solar cycle 24 as the Sun was moving towards solar minimum. This meant cosmic ray levels were already elevated inside the heliosphere before Voyager crossed. But even so, the jump from inside to outside was dramatic, a clear demonstration that the heliopause itself acts as a barrier even when the heliosphere is at its weakest. Voyager 2, which crossed the heliopause during solar minimum, detected an even larger cosmic ray increase, roughly 60% within the first month and a factor of 4 within the first year. This suggests that the effectiveness of the heliosphere as a shield depends not just on location where you cross, but also on timing when you cross. In 2023, Voyager 1 detected an unusual event, a sudden drop in cosmic ray intensity lasting several days, followed by a return to normal levels. The cause was traced back to a coronal mass ejection from the Sun that had occurred 2 years earlier. The CME had traveled outward through the heliosphere, crossed the heliopause, and continued into interstellar space, creating a temporary bubble of solar plasma that pushed cosmic rays aside as it expanded. Voyager, sitting in interstellar space, measured the shadow of this bubble as it passed a brief respite from the galactic radiation. This event confirmed something important. The heliosphere doesn't just block cosmic rays passively, it actively fights them. Every solar eruption, every burst of solar wind pushes back against the galactic environment, creating temporary disturbances that propagate into interstellar space and reduce cosmic ray levels locally. The heliosphere is dynamic, constantly adjusting, constantly responding to the Sun's activity, but the heliosphere is also weakening. Data from the Parker Solar Probe, launched in 2018 to study the Sun up close, shows that the solar wind has decreased in speed and density by about 30% compared to measurements from the 1970s. This weakening means the heliosphere is shrinking, the heliopause is moving inward, closer to the Sun, and the shielding effectiveness is declining. If this trend continues, cosmic ray levels inside the solar system will gradually increase. The change will be slow, perhaps 1% per decade, but over centuries it could become significant. For Earth protected by its magnetic field, the effect will be minimal. But for spacecraft operating in the outer solar system, and for any future colonies on Mars or the Moon, the increase in radiation will be a growing concern. The heliosphere, it turns out, isn't just a curiosity, it's a necessity, a living shield powered by the Sun that makes the solar system habitable. And Voyager, by crossing it, has given us the first direct measurements of what lies beyond a galaxy filled with radiation, indifferent to life, relentless in its energy. But the heliosphere isn't just made of solar wind and magnetic fields. It's also filled with matter, dust, and atoms drifting between the stars, ancient remnants of stellar explosions carried by currents we're only beginning to understand. Space isn't empty. Even in the vast distances between stars, there's matter, thin, sparse, but present. Hydrogen atoms a few per cubic centimeter, helium even less, and dust, tiny grains of solid material, each one smaller than a bacterium, drifting through the galaxy at tens of kilometers per second. Voyager 1 and 2, as they crossed into interstellar space, became the first spacecraft to directly sample this dust. Not intentionally, Voyager has no dust detector, but inadvertently through the impacts. Every few weeks, a grain of interstellar dust strikes the spacecraft's body, traveling at 56,000 kilometers per hour relative to Voyager, and the impact creates a tiny pulse of electric charge that Voyager's instruments can detect. These pulses, recorded over years, have allowed scientists to measure the density, composition, and velocity of interstellar dust in the region around the heliopause. The density is low, about 1 dust grain per 10 million cubic kilometers. Compare that to the density inside the heliosphere, which is even lower, 1 grain per 100 million cubic kilometers. The difference is subtle but measurable. And it tells us something important. The heliosphere acts as a filter, blocking some of the interstellar dust from entering the solar system. The filtering happens because dust grains, unlike atoms, have significant mass. As they approach the heliosphere, they encounter the solar wind, a stream of charged particles flowing outward from the sunday. The dust grains, though electrically neutral, overall contain charged particles within their structure. and these internal charges interact with the solar wind, creating a drag force that slows the grains down and deflects their trajectories. Small grains, those with diameters less than 1/10 of a micron, are deflected entirely. They bounce off the heliosphere, unable to penetrate. Larger grains, those with diameters greater than 1 micron, can push through, but their trajectories are bent and their velocities are reduced. Only the largest grains, several microns across, pass through the heliosphere, essentially unaffected. Voyager's data confirms this filtering effect. Inside the heliosphere, the dust grains that Voyager detected were predominantly large, greater than 1 micron in diameter. Outside the heliosphere in interstellar space, the distribution shifted towards smaller grains, matching the expected size distribution of interstellar dust in the galaxy. But what is this dust made of? The answer comes from spectroscopy, analyzing the light absorbed and emitted by dust grains in other parts of the galaxy, and from laboratory simulations that recreate the conditions of interstellar space. The dust is primarily silicate compounds of silicon and oxygen, similar to sand mixed with carbon in various forms, amorphous carbon, graphite, and even tiny diamonds, each one only a few nanometers across. The silicate grains form in the atmospheres of dying stars, red giants and supergiants that puff off their outer layers as they approach the end of their lives. These layers, rich in silicon, oxygen, and metals, cool as they expand, and the atoms condense into solid grains that drift into space. The carbon grains form in different environments, some in the atmospheres of carbon-rich stars, others in the shockwaves of supernovae, where temperatures and pressures are high enough to forge diamonds from carbon vapor. Once in space, these grains drift for millions of years, gradually accumulating a coating of ice water, ice methane ice, carbon dioxide ice, formed when atoms and molecules in the interstellar medium freeze onto the grain's surface. This ice mantle can be several times thicker than the grain itself, turning a tiny speck of silicate or carbon into a miniature snowflake a few tenths of a micron across. Voyager, passing through this dust, is essentially sampling the residue of ancient stars, grains that were ejected into space long before the sun was born, that have drifted through the galaxy for eons, and that now happen to cross paths with a tiny spacecraft from a young star system. The dust isn't just a curiosity. It plays a critical role in the galaxy's ecology. Dust grains absorb starlight, heating up and re-radiating the energy as infrared light, which warms the surrounding gas. This heating regulates the temperature of the interstellar medium, preventing it from cooling too much and collapsing under its own gravity. Dust also provides surfaces where atoms can meet and bond, forming molecules, including water, ammonia, and organic compounds that wouldn't form efficiently in the gas phase alone. In molecular clouds where new stars are forming dust, grains are the seeds of planets. As the cloud collapses under gravity, the dust collects in a disk around the forming star, and over millions of years the grains collide, stick together, and grow first into pebbles, then into boulders, then into planetesimals, and eventually into planets. The dust in your body, the calcium in your bones, the iron in your blood, the silicon in your cells, was once part of grains like these, drifting through the interstellar medium until 4.6 billion years ago. When the molecular cloud that would become the solar system collapsed, and the dust collected into a disk, and the disk coalesced into Earth. Voyager 2, which crossed the heliopause 6 years after Voyager, one detected a slightly higher dust density than Voyager, one about 20% more impacts per unit time. This difference is consistent with the asymmetry of the heliosphere Voyager 2 crossed in the southern hemisphere, where the heliosphere is narrower and where the filtering effect is weaker. More interstellar dust makes it through, resulting in a higher density. But the dust isn't evenly distributed. Voyager's data shows variations in the dust impact rate over time periods of higher activity, followed by quieter periods, suggesting that the interstellar medium isn't homogeneous. It has structure clumps of higher dust density separated by voids of lower density, all drifting through space at slightly different velocities. In 2024, analysis of Voyager 1's dust impact data revealed an interesting pattern. The dust grains are aligned. Their velocities aren't random, they're all moving in roughly the same direction parallel to the interstellar magnetic field. This alignment suggests the dust is being guided by the field. channeled along magnetic field lines like iron filings aligning with a bar magnet. This channeling has implications for the structure of the interstellar medium. If dust follows magnetic field lines, then the distribution of dust traces the distribution of magnetic fields. And if magnetic fields are organized, threaded through the galaxy in coherent structures, then the dust is organized too, forming filaments, sheets, and lanes that stretch across light years. Observations from other telescopes, including the Herschel Space Observatory and the Planck satellite, have confirmed this picture. The interstellar medium viewed in infrared light emitted by dust shows a web-like structure, long filaments of dense gas and dust connected by thinner strands, forming a cosmic scaffolding within which stars and planets are born. Voyager, by measuring dust impacts directly, is providing ground truth data for these large-scale observations. It's showing us what the interstellar medium looks like up close, at the scale of individual grains, and confirming that the structure visible from afar, the filaments, the clumps, the magnetic alignment, extends down to the smallest scales. But dust, as important as it is only one component of interstellar matter. The vast majority of the mass between stars is gas, hydrogen, and helium, mostly. And that gas, like the dust, has structure, velocity, and history. And Voyager, as it continues its journey, is beginning to measure that gas, directly revealing the composition and dynamics of the medium through which the heliosphere moves. The question now is, what happens when that structure changes? When the sun moves from one region of the galaxy to another, denser or thinner, hotter or colder. Voyager 1 and 2 were built in the 1970s, during an era when transistors were hand-soldered, when computer memory was measured in kilobytes, and when the idea of a spacecraft lasting more than a decade seemed optimistic. The design specifications called for a 5-year mission, maybe 10 if everything went perfectly. And yet, 47 years later, both spacecraft are still functioning, still transmitting data from the edge of interstellar space. The power source is what makes this possible. Radioisotope thermoelectric generators, RTGs, devices that convert the heat from radioactive decay into electricity. Each Voyager carries 3 RTGs fueled by plutonium-238, which has a half-life of 87 years. When Voyager launched, the RTGs generated about 470 watts of electrical power. Today, they generate about 250 watts, a loss of roughly 0.78% per year, steady and predictable. This power runs everything: the computers, the instruments, the radio transmitter, the heaters that keep the spacecraft's electronics from freezing in the 270 degrees below 0 Celsius cold of space. But the power is finite, and it's running out. By 2025, Voyager's power will have dropped below the threshold needed to run all the instruments simultaneously. NASA will have to start shutting systems down, one by one, prioritizing the most critical instruments: the plasma wave detector, the cosmic ray detector, the magnetometer, while turning off the heaters, the cameras, and eventually the backup systems. By 2030, the power will be too low to run even the priority instruments. The spacecraft will go silent, one by one, their transmitters shutting down as the last of the plutonium's heat fades. Voyager 2 will likely go first, having launched 16 days before Voyager 1, and therefore having depleted its power supply slightly sooner. Then Voyager 1 will follow, and after that they'll drift, silent, dark, coasting through interstellar space at their current velocities, about 17 kilometers per second for Voyager 1, about 16 kilometers per second for Voyager 2 forever, or as close to forever as anything human-made can be. The spacecraft won't stop. There's no friction in space, no air resistance, nothing to slow them down. They'll continue on their trajectories unchanged for millions of years. Voyager 1 is heading toward the constellation Ophiuchus, and in about 40,000 years, it will pass within 1.6 light-years of the star Gliese 445, a red dwarf, dim and unremarkable. But the closest stellar encounter Voyager 1 will have for the foreseeable future. Voyager 2 is heading in a different direction toward the constellation Andromeda, and in about 300,000 years, it will pass within 4 light-years of the star Sirius the brightest star in Earth's night sky, though. By the time Voyager arrives, Sirius will have moved, and the constellations will have shifted, and Earth's night sky will look nothing like it does now. But the spacecraft themselves will be intact. Space is vast and empty. The odds of Voyager colliding with anything, a star, a planet, even a dust grain large enough to damage it, are vanishingly small. Barring an extraordinarily unlikely encounter, Voyager will survive for billions of years, outlasting the Sun, outlasting Earth, possibly outlasting the galaxy's current structure, and each spacecraft carries a message, the Golden Record, a 12-inch gold-plated copper disc, etched with images and sounds of Earth, encoded in a format that any sufficiently advanced civilization could in theory decode. The record contains 116 images, photographs of people, landscapes, animals, cities, scientific diagrams. It contains 90 minutes of music. Beethoven, Bach, Chuck Berry, traditional songs from around the world. And it contains greetings in 55 languages from ancient Sumerian to modern Chinese, each one a voice saying, in essence, we were here, we existed, we thought, we felt, we created. And we hoped, however, irrationally, that someone someday might find this, and no, the chances of the record ever being found are realistically zero. Space is too large. The distances between stars are too vast, and Voyager, as fast as it is still moving at a crawl compared to the scale of the galaxy. Even traveling for millions of years, it will only cover a tiny fraction of the Milky Way's volume. The galaxy contains 400 billion stars spread across 100,000 light-years. Voyager, in its entire existence, will pass near perhaps a dozen stars. The odds that any of those stars host intelligent life and that life happens to detect and intercept Voyager are so small as to be negligible. But the Golden Record wasn't really meant to be found. It was meant to be sent. It was a message to ourselves, as much as to anyone else, that we could imagine a future beyond our planet, beyond our species' lifespan. That we could create something designed to outlast us. That we could, however, symbolically reach across the void and say, here is who we were. The record's cover includes a diagram showing the position of the Sun relative to 14 pulsars rapidly spinning neutron stars that emit regular pulses of radio waves. The diagram acts as a map, allowing anyone who finds the record to trace Voyager's origin back to our solar system. But pulsars slow down over time, and the diagram's accuracy degrades as millions of years pass. Eventually, the map will be unreadable, the pulsars unrecognizable. Voyager's origin will be lost, and the spacecraft will become an anonymous artifact, a relic of an unknown civilization. And yet, it will still be out there. A small hexagonal spacecraft covered in gold foil and instruments drifting through the darkness. A piece of Earth, forged from metals, mined from the ground, shaped by human hands, launched by human ambition, and now part of the galaxy's fabric. A messenger with no destination, a monument with no audience. The engineers who built Voyager, many of them now in their 70s and 80s, still monitor the spacecraft from NASA's Jet Propulsion Laboratory in Pasadena, California. Every day, they download the latest data transmitted across 23 billion kilometers at a rate so slow that a single image would take hours to receive. The signal, by the time it reaches Earth, is weaker than a watch battery. But it's there, and as long as the power lasts, they'll keep listening. In 2023 and 24, Voyager 1 suffered a serious malfunction. A memory chip in the flight data subsystem, the computer responsible for packaging science data for transmission, failed, causing the spacecraft to send gibberish instead of data. For 5 months, Voyager 1 was effectively silent, unable to communicate its measurements. The engineers, working with hardware schematics from the 1970s and code written in a programming language no longer widely used, diagnosed the problem remotely and devised a solution. They rewrote part of the spacecraft's software, uploaded the new code, and successfully restored communication in April 2024. The fix required weeks of work, uploading commands in small chunks to avoid overwhelming the spacecraft's limited memory, and waiting 22 hours for each command to reach Voyager and another 22 hours for the Sension response to come back. It was a surgery performed at interstellar distances on a patient built before the invention of the microprocessor by a team of engineers who had already retired once. That moment when Voyager 1 began transmitting data again after months of silence was both a triumph and a reminder the spacecraft are dying. Slowly, inevitably, they're running out of time. The instruments are failing. The heaters are being turned off to conserve power. The transmitter, which once broadcast at 23 watts, has been reduced to lower power modes to extend the mission by a few more years. NASA's current estimate is that Voyager 1 will lose power by 2036. Voyager 2 by 2034. After that, the Deep Space Network, the array of massive radio antennas that receives Voyager's signals, will point toward the spacecraft's last known positions and listen, hoping for a final transmission. But eventually the signal will fade, the spacecraft will go silent, and Voyager will become what it was always destined to be: a traveler without communication, a probe without a purpose, a piece of human technology adrift in the infinite. But the data Voyager has sent back, the measurements of the termination shock, the magnetic highway, the heliopause, the interstellar medium will remain. The discoveries will endure in human knowledge, shaping our understanding of the sun's environment, the galaxy's structure, and the boundary between the two. Voyager revealed that the edge of the solar system isn't a line. It's a zone dynamic complex, full of structure and surprises. It showed us that the heliosphere is asymmetric, squeezed by forces we didn't fully appreciate. It measured the heat of the termination shock, the hum of the interstellar medium, the surge of cosmic rays beyond the heliopause. It detected the dust between the stars, the magnetic filaments threading through space, the echoes of ancient supernovae. And it did all this with technology from the 1970s. 68 kilobytes of memory, a radio transmitter weaker than a cell phone, instruments built by hand, tested in vacuum chambers, and launched on a trajectory that could never be repeated. Voyager's launch window, the alignment of the outer planets that allowed the spacecraft to visit Jupiter, Saturn, Uranus, and Neptune in a single mission, won't occur again for another 176 years. Voyager is a product of a specific moment in history, a time when humanity looked outward, when resources and ambition aligned to send machines into the unknown, not for profit or survival, but for curiosity, for the simple, profound desire to know what's out there. And now we know, at least a little. We know the solar system doesn't end abruptly. We know the sun's influence fades gradually, blending into the galaxy's background over a zone that spans tens of astronomical units. We know the galaxy isn't empty. It hums, it flows, it presses against us. And we know that the heliosphere, fragile and dynamic, is what keeps us safe. Voyager, in its final years, will continue to measure the cosmic rays, the magnetic field, the plasma waves, and every piece of data it sends back will refine our understanding, adding detail to the picture, correcting the models, revealing the unexpected, until one day the signal stops, and Voyager becomes a memory, a story we tell, a tiny spacecraft alone in the dark, carrying a golden record no one will ever play, moving towards stars no human will ever see. It's the loneliest thing humanity has ever created, and also the bravest.